So the last thing that we're going to look at is concentration. And this is basically mostly math, and you've done most of it before. So you can say real simply if something is dilute or concentrated, but we don't do that very often. I mean, you can, but it's not very quantitative, and in chem, you're usually quantitative. So we don't say that very often. You've seen probably percent composition before, and what you do is you do your part. Sorry, I'm going to write really bad because I'm not using the board. So part over whole times 100. You use this a lot in stuff that doesn't really, isn't very mathematical. They use it a lot in biology. We don't really use it that much in chem, but it is a way to do it. We all know molarity, or we should all know molarity, is your moles over your liters. To see basically how many moles are there present. And those are the ones we'll use the most. The one that you haven't seen before is probably molality. People use molality because technically your volume can change with temperature, but with molality you're not using volume, so you don't have that influence. So if you're doing molality, it's like a fancy M. And molality is your moles of your solute over, again, my handwriting's atrocious right now, your kilograms of solvent. The very last thing is mole fraction, and you're just literally figuring out total moles, each moles. And again, I don't know why they ran out of M's or something, but they use X for this. And they typically do mole fractions mostly with gases because that's going to help you with PV equals nRT. But if you're doing this guy, it's going to be your moles of what you're looking for. So I'm going to say component all over, oh, again, horrible writing there, total moles. So those are the 4 major ways we're going to do it. We'll do an example of each one, and then that will be done. All right, so if we look at number 1, they want us to calculate our mass percentage. So what we want to do is, this is wrong. There's a mistake, so you want to fix this. This should not say kilojoules, it should say kilograms, so that's my own fault. So if we're going to do percent composition, basically mass percent, we're going to do our polar part, which is, I'm up too high, 13.6 grams, over our total. So if we look at this for our total, we have 100 kilograms, or 0.1 kilograms, which is 100 grams. And we also have 13.6 grams. So our total is 113.6. And all I did is I just turned them into the same unit, added them together. Times 100. And we should get 11.97. So 12.0 is sig figs. Again, atrocious writing, but 12.0%. Just going the opposite direction here, we have a commercial bleaching thing. It's 3.62% sodium hypochlorite. We want to know what's the mass of sodium hypochlorite in 2.5 kilograms of bleach. So it's very similar, just a little different. We know we have 3.62%. Is going to equal the amount that is actually in there over our total, which is 2.5 kilograms, or we probably just want to put it in grams to make it easier, 2,500 grams. And remember, this is times 100. So all we're going to do, we're going to divide by 100, multiply by 2,500, and what we're going to get with sig figs is that in bleach, there's approximately 90 grams our sodium hypochlorite. So it's same process, just different way of looking at it. For molarity, again, you've done this before, but you're just getting moles and stuff. So if I'm doing molarity, I have 8.5 grams. And I know that 1 mole of calcium nitrate, when I look it up and write my formula and everything, is 164.1 grams. And then I want to divide that by my total liters. So I'm just going to say 1 over my 2 liters. And I should get a big long decimal, like 0.025, 8, kind of stuff. But then when you actually round it down, you should get 0.026 molarity. Number 4, again, is just a different way. We know molarity, now we're working backwards. So what we're going to do is use our molarity equation. We have 3.67 molarity equals X over the 1.25 liters. And then whatever we get for X, we're going to multiply by its molar mass. So there's 111 grams in a mole. So I don't even know if I can get it here, but what this X equals is 4.59, and that's moles. So we multiply that by 111, and you get around 509.67. And if you round it, 5.10, I'm sorry, I can't write, 510 grams of your solution. There's supposed to be a circle, sorry. We have molality and mole fraction left. So molality, again, you're just doing your moles of the one thing over kilograms of the other. So the first thing we're going to get moles of NH3, because that's definitely our solute, it's smaller amount. So we just take our amount, just 0.850, 1 mole, 17 grams, and we get 0.0500 moles. And then to actually calculate molality, we get 0.050. So again, that's our moles of solute over our kilograms of solvent, which is 0.125 kilograms. And with sig figs, that is 0.400, and molality is the fancy M. For naphthalene and toluene, it's the same exact thing. So first thing we're going to do is just get naphthalene is the smaller component, so that's our solute. So we take 36.5 grams. 1 mole is 128 grams. That's going to equal 0.285 moles. And then that means our molality is 0.285 moles over our kilograms of solvent, which is 0.425. And that should equal 0.671 molality. This will be really important for the last thing in our chapter, which is about, we're going to do colligative properties, which is when we make the ice cream lab. So you want to understand how to do this, because this is the ice cream lab coming up. And last but not least is mole fraction. So I need 2 slides for this, because I know I'm going to write big. The first thing you do when you do a mole fraction is you have to calculate moles. So I'll do the first one, and then I'll just give you the answers for the other ones. But I'm going to do the C3, the methanol, CH3OH. I'm going to say that 1 mole is 32 grams. And I get 1.31 moles. So you do the exact same thing for the ethanol and the propanol. So this was, wait, let me write this one. This one was CH3OH. So the next guy, C2H5OH. When you calculate him out, you should get 0.761 moles. And for C3H7OH, you should get 0.833 moles. So when you do mole fractions, you're going to do your part over your total for each one. So what I'm going to do is just do the same thing for all of them. We do need the total though, so I'm just going to say what our total is over here. When I add these all up, I get a total of 2.904 moles, which we'll need to use, if I added that up correctly. I think I must have carried out some more decimals in that one. All right, so I'm going to do my mole fraction of CH3OH. And what that looks like is I take my moles, which was 1.31, divided by the total, and we get 0.451, which is basically saying 45.1% of the moles comes from this. For the next guy, it's going to look very similar. Same overall total. And he's going to equal 0.262. And last but not least, when we divide them out, we get 0.287. Oh, that should say 7, not 9. 7. When you add them up, they should add up to 1 because you're basically getting a percentage, and you do for this one. So that's what you want.